this recording again. I can always record tomorrow, so if it fails. But anyway, all right. Yeah. So as I was saying, we already discussed the difference between supervised learning and unsupervised learning. Essentially, in one case we have labels, in the other we don't, right? So we covered the KNN algorithm, but one key concept here is that KNN and K-means are similar. They have different objectives, but they are different. But they are similar algorithms, or because of the medium. So they're both based on the vector space model. So that means that every sample is essentially represented as a vector of size n, whatever that is, and then all of those represent points in a vector space. Okay? And so in the previous example, we were learning how to do classification in this space given the labels. Today we're going to learn how to apply the K-means algorithm for unsupervised learning. All right, so that's our goal for today. And this is this should be an interesting. I'll provide two examples of this. But it should be a very interesting set of ideas. And one of the examples will relate to cybersecurity, to network security. We'll continue with our original idea from the beginning of network intrusion. Right. So we have packets. Once again, and if you remember, at some point, I only focus on the IP header and TCP header of the packet. Today we will focus on the payload, right? So as you guys know from your networking classes, you'll have payloads that have just the text that's being transported. So that should be an interesting one. So I have some code here. We'll do two examples. One will be a simple example with language. Okay. So we'll do language, a few sentences. And then after that, and there's a lot of concepts. Today is not so much an algorithm, but we're just going to look at a complete pipeline, and we're going to introduce the sklearn library, which will allow us to use K-means. Okay, I do have some slides, and this is just to give you an idea of the algorithm. If time permits, I may at some point come back and we'll implement K-means from scratch. Okay. But that's not really the goal. But I'm going to describe it just a little bit just to let you guys see how it works. So I'm going to click on this PowerPoint presentation here. I'm going to download it. And we're just going to talk about it. So there's a few terms here. So there's unsupervised learning, right? The algorithm is called K-means, which sometimes people confuse it with KNN, right? Because they're similar, and they are. But just remember there are two algorithms. And essentially, K-means does something called clustering, okay? So that's something really important. So, just by looking at you guys and your distribution here in this classroom, I can say, okay, there's two clusters. This cluster over here and that cluster over there. Do you guys see that? But what if I just say I want three clusters? Okay, if I want three clusters, then likely like that group over there, you guys in the middle, and then that group. Do you see that? So I could also create 20 clusters. All right, so it's an algorithm, it's very powerful. And a lot of these things we can do as people, but we don't really know how we do it, right? It's just our minds can do it. But there are algorithms that can also simulate some of these tasks. All right, so let's take a look at the slides here. And like I said, just to get it should be a good presentation, just to get an idea of how it works. It's very powerful and very useful. Sometimes you have data, but you just don't have anything to label, right? So essentially, let's talk a little bit about this, okay? So clustering or unsupervised learning. So this is the goal with supervised learning, okay? And remember that we had the discussion on the vector space model, and I gave the example like we have one dimension, a plane, two dimensions, a Rubik's cube, or this classroom, three dimensions, and mathematically we can have spaces that have 10,000 dimensions, right? We've talked about that. So the math holds, and I showed you guys that. So everything in this example, obviously to keep things simple so that we can visualize it, we have a two-dimensional space, x and y. So every point is just represented by two values, so age and weight. That's it. So all of you are represented by just that. So I can represent you as points in a vector space of two dimensions, this plane. So we've talked about that. So I'm just using that for simplicity, but obviously it can be many dimensions. 20, 40, doesn't matter. All right, so in supervised learning, we have all the points, but we also, for each point, have a label, right? Remember, so we have our x and our y values. So here I have an x and a y, an x and a y, an x and a y. So that's why I know that these circles, I can draw these points as circles, blue, and then I can draw these points as red x's. You see that? Because I know that I have this label, okay? In fact, unsupervised learning does not have these labels. Okay, so that's the key thing. So it's still the same vector space, still every point is a vector of 2, but I have no labels. So I would have no way of knowing that these are circles and these are x's. Okay, when I have that information, then I can implement something like K and N, right? K and N essentially has a goal similar to this, finding something like a blue line. Think of this. K and N doesn't actually do this, but just think of it right now intuitively, right? It's almost like it's trying to figure out a line somewhere that separates between the two groups, okay? That's kind of a good intuition. Unsupervised learning is this other approach, still the same thing, points in the same vector space, but notice they're now not circles or x's, they're just all points because I have no label associated with them. That's it. That's the whole difference, okay? So now notice, before I had x and y, now I only have x, x, x. So I have the data. All right, so it's the same thing. I group you guys by weight and age, right? But what do I do with that data? Do you see that? So all I can do is maybe start to analyze the data, and one of the techniques is I can just cluster you guys, right? So, if we had children, right? So they would be on average around 10 years old, 9 years old, versus you guys are probably around 22 years old, something like that. So obviously I can find a mean of all of you for that particular variable, and I can start grouping it. Do you guys see that? And I can do that for all the variables and so on. So that's essentially what it is. So we have this algorithm called KMeans, and it just does clustering for us because we don't have the labels, but we can still do some type of analysis. So here, as somehow magically my brain can look at all these dots and say, yeah, I would draw a circle here and a circle here, right? How do we do it? We don't even know, right? Our brain just does that. But as it turns out, we can use math and things like that to figure this out and get the exact same answer. Okay? All right, so what are the applications of clustering? Clustering is very important. Market segmentation, so people in marketing, advertisement, they're obviously doing this. All that they say they collect all of your personal information, right? So think about that. So you're all vectors in someone's vector space, and they're just clustering you, and then based on the cluster that you fall in, boom, advertisements, right? So that's something very obvious. Social network analysis. Many of you are probably on social networks, your friends, all your connections, your interests, all of that, groups and so on, same thing. You become a vector in a vector space, they're clustering you. And then advertisements, or whatever it is. Organized computer clusters, so this, you can imagine a whole bunch of computers again, right? Represented as vectors, things like, whatever latency or RAM usage or whatever, and they get clustered in a pool, and then they get allocated depending on needs. And obviously, there's a lot of data in astronomy, science, etc., and so you can use that information, the stock market, no doubt, all kinds of things like that. All right, so many applications. Today we're going to apply this to language, and I'll show you some insights into it. And also, like I said, we're going to do a cybersecurity example. But you'll see, they have things in common. All right, so the algorithm. So let's look at it. We're just going to look at this from a high level, so we're not going to get into the code, but I'm just going to give you a basic idea of how it works. All right, so here you should be seeing it. I have a little graph. So this is a vector space of dimensionality 2. Notice that this one's a little bit harder to tell, right? But if I want 2 clusters, I would probably draw one around here and one around there. Do you guys see that? So that's essentially the algorithm. So that's essentially the problem. Now, the algorithm is simple. Since I want 2 clusters, I have to kind of randomly pick 2 points in the space. Just pick 2 points randomly and say those are the means, okay, of data. So there you are. I pick 2. These are called the centroids, by the way. So I want 2 clusters, so I pick 2 points randomly. Boom. Those are the centroids, and then guess what? I used the Euclidean distance, right, to measure the distance between this point and all other points. And based on those distances, then now I know which points are closest to the red one and which ones are closest to the blue one. Do you guys see that? So that's essentially what happens. So I calculate that, and now it kind of does something like this. You see, because, yeah, it makes sense that these red ones are closer to this x, and these blue ones are closest to the blue x, right? So it did that. So what do you do now? Now that you have these 2 groups, you essentially can assign some kind of temporary label to these points, right? That's now possible, right? So you know these are labeled, red, these are labeled blue, and what do you do now? You calculate a new centroid for the blue and a new centroid for the red. You know that initially it was just a random one. Well, now, as it turns out, you have a slightly better one. Do you see that? And now you have a new centroid for each of the 2 clusters, and then guess what? You just repeat the process again. So for those given centroids, you calculate all the distances to find out which points are the closest to those points. And then guess what? I don't know if you guys noticed, it switched a little. So notice like here at the top, see it changed to blue a little bit. And so you just repeat this process and you keep repeating it until you have a better cluster. So now you'll do the same thing, calculate centroids. There they are. The data moves. You see that? How nice that is. One more probably. Notice now the centroids move a little bit because it's like the centroid is being pulled by the points. And yeah, so that that kind of gives me my 2 clusters. So I have one cluster here and one cluster there, and you can do this for like 1,000 iterations or whatever, but that's essentially the process. This is in fact something that, with your understanding of KNN, I think you could actually implement this algorithm from scratch, right? So it's something that's it's not such a big deviation from what we did in KNN. So as time permits, I may come back to it or not. All right. Any questions on this technique? Clustering with the vector space model. So that's it, right? So now that we know this technique, let's try to implement it. And then here, if you'd like, you can go over the algorithm. It's described, so you can read through it. But we went over it. All right. So that pretty good, I think, discussion. Now we're going to get into implementing a pipeline of machine learning with some data so that you can see how to use it. Like I said, I have 2 examples for this one. So we can click on code, and we'll be using Colab for this example. All right, as you can see, I have 2 links here. So the second link is the network security one, so we'll leave that as a second example. We'll start with a more obvious one that's easier to understand. Yes? Yeah, you use Colab for that one. Yeah, just use Colab. All right, so we're going to use Colab for this one as well. I'll start with this example, so you can just click on it. Okay, and here it is. All right, this is a whole pipeline of various things that we can do, but we're going to try to implement kind of the clustering ourselves, from the data. Okay, so let's go ahead and open up Colab. All right, and I'm going to open a new notebook here. Okay. So let's go ahead and bring in some of the libraries. Give it a minute. All right, so as you can see, some of the same libraries that we used last week. We've got sklearn, pandas, and NumPy. We have something here called from sklearn, the count vectorizer, and that's because we're going to be using strings, right? So you'll see in a second, our data is actually going to be sentences. Similar to how, well, not similar, but I guess within the realm of ChatGPT, right? So you guys, I'm sure, have used ChatGPT. You type text, something happens, you get text, right? So, but in the background, you have machine learning algorithms, AI. So this is essentially before ChatGPT, but I'm going to show you guys how text can be represented as vectors as well. So and we're just going to do it with this nice library count vectorizer. Also from sklearn, we're going to take a look at something called the truncated SVD, singular value decomposition. If you guys remember, I said we're going to cover singular value decomposition. We're using it here today. We'll get into a little bit of the details of the algorithm and then try to apply it to the recommender system problem or something called collaborative filtering. All right, and then here we have matplotlib, obviously, for plotting. So you may have seen matplotlib in 265. Notice that we're using sklearn quite a bit in this example. So sklearn is something that you should be aware of. It's definitely a very powerful library, and sometimes it can help you. There may be an sklearn homework at some point later. Okay, it should be pretty straightforward. You don't implement the algorithm like we did with KNN. You just use. So it's somewhere in between Weka and what we did with KNN, right? So you still code, but you have libraries that you can treat the algorithm essentially as a black box. So it's definitely something that you should be aware of. So we're using truncated SVD as part of the pre-processing, so not as a machine learning algorithm, but just as pre-processing. Count vectorizer as pre-processing. Yeah, okay. And then sklearn, we're gonna use from it the K-means algorithm. All right, so let's go ahead now and take a look at the data. So this is going to be our data. Okay, so as you can see, I have in this, just small amount of data. I have, in fact, I think 1, 2, 3, 4, 5, 6, 7 sentences. Okay, and I need to somehow represent these sentences as vectors in a vector space, right? So we've talked about how I'm going to cluster, right, things as, they're going to be points in the vector space. So how do we essentially do that? But before we talk about that, let's just read through the sentences, right? And you guys tell me how many clusters you see and what would you name those clusters. So I have 7 sentences. First one says machine learning and Python are super fun. Second one, Python is super, super cool. Number 3, statistics and data science are cool too. Number 4, data science and Python are fun. Number 5, Python is great for machine learning. Number 6, I like football and it is great. And the 7th sentence, football is great to watch and I like it. So if you had to tell me, how many clusters do you see here and what would you label them? Just from reading these sentences. Anyone? There's 7 sentences. If you had to group the sentences, yes, sir, Van. For sports, okay, so you see 3 clusters, right? So you see one for Python, one for data science, and one for sports. Great, so that's 3. It now, if you only can do 2, then what would they be, sir? Okay, right. So the first 5, right, would belong to one group, and then the last 2 would belong to another group. Right? Exactly. That's good, right? So that's essentially what we do as people, right? But now we're going to have an algorithm do that for us, right? So let's see if we can be successful. So there's going to be some challenges with this, but you know, I'm going to have to do a trick to make it work, but actually that can help you out to understand. Keep in mind, these algorithms do require some amount of data. I only have 7 sentences here, right? So having more sentences would provide better results. But yeah, so we're going to do that. The other thing, but so now that's great. We have the sentences, we know the problem. The question is, how do we represent these, right? So that they can be points in a vector space model. So I will use the whiteboard for this, but I'll show you this first. All right, so I'm going to, like I said, I'm avoiding writing algorithms from scratch. Keep in mind, I'm using like 4 different algorithms here, but we're just using the object, right, that represents those algorithms. So the first one is I'm going to instantiate a count vectorizer, right, and it's going to be for English. So that means essentially that it can look at words now, words in English, and it'll be able to do something to process these sentences. Okay, so I instantiate the vectorizer. Then notice I'm using sklearn's approach that you can both train and run an object at the same time. So here I'm taking what I just instantiated, the vectorizer, and I'm going to say, all right, fit transform on examples. What is examples? The 7 sentences. Okay, so I'm going to do that, and I create an object called DTM. All right, so I've created DTM. And now I'm going to go ahead and try to plot DTM. All right, notice I'm using pandas just for better formatting, so things look nice. I'm going to create a data frame, okay? I'm taking DTM as input and I'm converting it to an array, okay? And then I'm going to say that essentially it's going to be a matrix of rows and columns, right? So the rows are now going to be the sentences, all right? So every sentence is a sample, essentially, in this example. So notice I'm saying index equal examples, the 7 sentences, and the columns of this matrix is going to be the feature names, all right, which are going to be the words. All right, I'm going to print about 10 of them. So if I do, do this, and you can see that there. So what am I doing? I'm essentially, because I want to create a vector space, right? I'm creating for every sentence a vector space of words, of the occurrence of a word. This technique is a technique that existed up until 2012, right? I mean, as the main approach, it was called the bag of words approach. So keep that in mind, right? So I'm sure people did research and advanced this a little, but the common practice up until 2012, right, was to represent the sentence always by this approach. Today we don't do that, and the change that was made is called embeddings, and that is one of the things that contributed a lot so that you guys can have something like ChatGPT today. But this approach was not the greatest, but still it can work, right? So that doesn't mean that it doesn't work for some applications. Notice essentially, so I have 1, 2, 3, 4, 5, 6, 7 sentences, and then for each sentence, I'm counting the number of times that I see that word in the sentence. And that's really important. So for instance, No, so the vector, the columns become each of the words. So obviously, Count Vectorizer went through the 7 sentences, identified all the unique sentences. It probably skips words like the, because the is going to appear in a lot of the sentence and not be so relevant to determine, what it is. So those are called stop words. But if you notice here, it's going to look and it says, okay, the word fun, I see it in there once. The word learning is present once. The word machine is present. The word Python is present. Super is also present. Do you see that? So it's essentially keeping account of the words that are there. But it assigns a 0 to the words that are not present. Okay? Now, in this example, for instance, I have Python is super, super cool. And you can see I have actually a count of 2. So it's counting the number of times a word appears. If you notice, there's a lot of zeros. So when you have a lot of zeros in a matrix, it's called a sparse matrix. Now, usually, if I was doing this with thousands and thousands of sentences, I would need to have thousands and thousands of words, right? So you can imagine then that the vectors become very big, right? Essentially the size of the vocabulary. So imagine if I have 50,000 words, every vector is 50,000. It's going to have a few ones, and most of the values are going to be 0. That's a big problem for machine learning that had to be overcome. And today we have a better way where the sentences would be represented by a small vector of, say, 256 values, and everything has a value. And those are called dense vectors. All right, but anyway, so we're back to this problem. So as you can see now, another thing that you can see is that the values here are almost like binary, or, a few counts here and there. But we can go to the whiteboard now and think about this a little bit. So we're going to go to the whiteboard. All right, and remember, we have 7 sentences, right? We have 7 sentences, sentence 1, sentence 2, all the way to sentence 7. Each of these is just a point. Imagine that. One sentence is just a point in a vector space. Let's say that we had like 20 words. I can't remember exactly, but let's say there's 20. So it's a space. We can say R20 in this case. Let's say it's 20 words. And there's literally 3, 4, 5, but they're all uncorrelated, right? So mathematically, it would hold that they are 90 degrees from each other, right? What is called orthogonal. We just, as we've discussed before, there's no way for us to visualize this, unfortunately. All right? But we'll do a trick to be able to visualize this, right? So it'd be nice, right? So we're talking about clustering, so intuitively, you guys want to see these points, some of them as green, some of them as red, right? But there's no way for me to visualize these points. Now, what I can say is that sentence 1, let's say, would be a point here. Sentence 2, a point there. Sentence 3, you know what I mean? So the sentences are definitely points in this vector space, but I cannot visualize it. There's no way that I can print anything that's 20-dimensional, okay? However, one thing we can do, which is what, because this is part of clustering, is we can do a transformation or a mapping. So every point, you guys agree, that is a vector, let's say, of size 20, right? So sentence 1, sentence 2. So they're vectors of size 20. There's no way we can visualize those points. We can only visualize things that are 2-dimensional or 3-dimensional. However, we do have in machine learning a couple of techniques for compression. You guys have seen feature ranking, right? So you saw that in Weka. So the equivalent of that would be to drop a few of the features, but there's a better technique called either PCA or SVD. I'll use SVD today, singular value decomposition, and this allows me to transform a vector from one size to another size. So essentially that's what it is, okay? So I can, for instance, map via SVD, I can map from vectors of size 20 to vectors of size 2 or 3. What's the advantage there? If I map to a, let's say, to a vector of size 2, now each point has 2 dimensions. So that means I can plot it. And so I can see the point. Now, there is one problem, and that is, of course, as you start reducing the dimensionality from, let's say, 20 to 2, you do lose information. That's the problem. So it's a trade-off. So for instance, it might be that you can downgrade it from 20 to 7 and only, you retain like 95% of the information. That's really great, right? But you still can't plot it. So if you're really, so what you might do is keep it at 20, reduce it to 7 to get some efficiency, and then if you want to plot it, go ahead. But maybe once you reduce it to 2, you're only able to retain 60% of the information. That means that now there's going to be more misclassifications, more errors, and so on. Does that make sense, guys? So, but really, visualization is not key to this process, okay? That's what you should understand. If you really just want to cluster your clients to, offer them ads and make money, the compression to 7 may be the sweet spot where you actually make the most money. And still, if you want to visualize it somehow for some analysis, you can go down to 2, but that's not, the optimal, right? And visualization is not necessary. Again, it might be that you want to present something interesting to your client, so here in this example it works really well, but it's not, this is kind of an academic example created just for you guys to see this. Okay? All right, so this is important concept. So again, today, my goal is not to cover PCA or SVD in detail. We'll cover a little bit of those things later in the semester. The actual algorithms are very interesting. Today, we're just going to use sklearn, which provide, and I'm showing you essentially that you can do a lot with sklearn, to solve this. Does this make sense, guys? So every point as a word. So essentially, this vector space is of words. There is one of these axes that is super. And another one of these axes is learning, right? You see that? But once you compress from 20 to 2 or to 7, you no longer, those words don't exist anymore. That's one thing that you should understand, right? The compression with something like SVD from 20 to 7 makes the words disappear. Okay? And now it creates these semantic concepts. But it might turn out, so for instance, let's go back to, let's share the screen. Let's go back here. It might turn out that, yes, it loses the word, here. So it loses the word cool and the word fun, but it creates just some concept that kind of is both words. You see that? So that's what's essentially happening in a statistical way. The algorithm is doing that. We just don't know what those things are. I mean, sometimes people study that and eventually it turns out that, there's cats and dogs and it just it seems that it made animals. You know what I mean? Like you have to kind of infer it, but that happens just because that's the underlying thing in the data, right? So remember, it's all driven by the data. All right, so so as you know now, we have our example, and every sentence is now a point in this vector space of about 20 words, okay? All right, great. So hopefully that makes sense. So we have 7 points, and now we want to create 7 not 7 clusters. We want to create 2 clusters, let's say, out of these 7 points. All right, so we've done this representation. Now comes in, as I said, singular value decomposition. Okay, so I'm going to just illustrate today how this works. Okay, so I have singular value decomposition. Notice I'm going to specify 2. You can actually use, if you have 20 words, right, you have 20 dimensions, you can use SVD to produce 20 dimensions. All right, essentially it's just copying what you had, and you retain 100% of the information. As you start saying, okay, I want fewer dimensions, that's when it needs to compress, right? So a good analogy is like you guys know about compression of images, right? So lossy, lossless. So you guys know that when you compress via JPEG or whatever, there's a bit of a loss of information, right? So it's something similar. And it's an algorithm that does this in the background. Here, I just want 2. Okay. All right, so I've instantiated the object. This is now a truncated SVD model, and now I'm going to apply my data to it. Notice I'm calling it LSA. I'm using the exact same approach, fit transform, so it's going to look at DTM. What was DTM? DTM is the data that I had here, this one, right? Notice we don't have to use PD because that's actually a data frame, a pandas data frame. So essentially this one, DTM, okay? So I'm going to apply it, and I'm going to call it DTM LSA. That just means that now my data has been processed, to be compressed. All right, so now we're going to go ahead and do kind of the same thing. We're going to use pandas to help us with visualization. Oops. So you can see here, I'm bringing in a pandas data frame again. I'm grabbing DTM LSA, okay, as input. I'm saying that, remember, it's still producing a matrix, right? So I need to specify it's still 7 sentences. But now my columns have changed. I used to have like 20 columns, right? 1 for every word. But now I've compressed it to just 2. Right? That's the power of singular value decomposition or the other algorithm, PCA. And later on, we'll see how this works. But essentially then, I create, and I'm going to call them because I no longer know what they mean, right? All that I can say is they're singular value, singular value 1, singular value 2. Singular value 1, singular value 2, right? And I'm going to have that. So here it is. Notice the difference, right? So before, I had 7 sentences, and every sentence was represented by a vector, right? And now I have 7 sentences, but now they're just vectors of size 2. And these are the values that were computed by the algorithm, for me to use. Take a look at the data for a second. Do you notice some kind of a trend? Remember, this is machine learning, data science, right? It's all about patterns. So look at that data closely. And let me know if you see some kind of a pattern emerging already in the data. Anything? Yeah, go ahead, please.
Wouldn't that be one as a high value with lower value and vice versa?
Okay, good. So yeah, so that's a good observation. So these seem to be like, higher, lower, lower, higher, right? So we start to see that. And notice also that there seems to be, these are higher, right? And these are lower. These are almost negative, and these are positive. And in relation to the sentences, it's like it's almost already seeing that there's a difference between these 2 last sentences and the first 5. Do you guys see that? So it's already, the data is already starting to capture that. Okay? So yeah, very good. So you can see that the algorithm, it's already helping us out to do this clustering technique. So let's now move on to the next step. So remember, this is still pre-processing. This is just one of those things for compressing our data. All right, and there's other applications for this, like many others. All right, so you can see we have that. As far as, you might wonder how this works, so we'll cover this later, but essentially, it becomes almost like a linear mapping. So every word of the 20 would receive some kind of a weight. Like, that's the algorithm of PCA or SVD. So it's like word 1 and some value plus word 2 and some value, and the sum of those gives you the new singular value that I just created. And so, it's essentially like it's looking at combinations of the words with different values, and then you just select a few of them that retain most of the information. This is just very high level for now. We will come back to this algorithm later in the semester, okay, these algorithms. All right, so now let's go ahead so now it's the advantage, right? We can plot this data, right? Because it only has 2 dimensions. If it was 3 dimensions, we could also plot it. So let's go ahead and plot it. Notice that I still haven't done any kind of, I haven't used the K-means algorithm at all, okay? So here, I'm going to grab, so remember, DTM LSA is this matrix here, right? DTM LSA is this matrix here. So it's got 2 values, right? So if I iterate, if I say for W and DTM LSA, essentially what I'm doing is I'm grabbing every row of the 7. But in each row, there's 2 values, right? There's this one and that one. So that's what I'm doing here. I'm grabbing the row, and then I'm just saying, I want row 0 versus row 1. And that's because I'm about to plot these values, so I want to have the values on the x-axis and the y-axis. So 2-dimensional, so I can actually plot every single point. Make sense? So essentially, I'm plotting these here. Okay, and I'm calling these x, xs, and these are called ys. And this is just how matplotlib wants its data, essentially. All right, so now I'm going to go ahead and plot it. I'm going to use from matplotlib something called a scatter plot. Notice I give it xs and ys, and I name the x label svd1, the y label svd2. All right, so if you look at that, these are the points. These are your 7 sentences. And now if I ask you guys, if you can give me 2 clusters, how would you draw them? 2 clusters, how would you draw them? Probably these 2 at the top, right? And then maybe these ones at the bottom. Somehow that's, intuitively, that's what our brain is saying. How we know how to do that, who knows, right? But that's what we want to do. So essentially now, what we need is an algorithm to do this for us, right? So we need an algorithm that can look at every point and say create 2 clusters, assign each point to a cluster, and then now we're going to have, in fact, a label. So it's funny because on K-means what it does is it makes an unsupervised data set into supervised. It's just going to assign labels to it. So let's call cluster 1. So all of these would have a label 1, 1, 1, 1, 1. And then let's call this cluster 2, and all of these would have a label 2, 2. Do you see that? That's essentially what we want, our goal. So visually we know this has worked, but what does K-means do? Go over here. So now notice the next step is I'm going to show you guys, today is like an important day in that I'm showing you for the first time how to use K-means to do machine learning, right? So it's now your 3rd tool in your toolbox, right? So you have Weka, you can write it from scratch with NumPy. Now you have a 3rd tool, which is sklearn. And this is definitely one of the easiest ways, so you should have some sense of how to use it, because we can just bring in any algorithm, KNN. We could have used this for last week, but our goal last week was to understand the algorithm. All right, so how do we do it? We invoke from sklearn the K-means algorithm. So from sklearn.cluster, that's the family, we invoke K-means, and then we just need to instantiate it. Usually there's a whole bunch of parameters, and we just go with the default ones. So here I'm naming the object KMLSA, and I'm instantiating the K-means algorithm, okay? Notice that I do have to say that I want 2 clusters. there is a way for you to like, sometimes the problem, you kind of know what the centroids would be, and that, having a better starting point is good. But when you don't know, you do random. You do about 10 initializations, so it's going to try maximum number of iterations is going to be 300. So a lot of these algorithms are just, repeating the same process, right? So you're going to have 300 iterations. This is for randomization. All right, so let's click on it. So now we have instantiated the K-means algorithm. Okay. All right, and now we can apply it to our problem. All right, so same approach, KM LSA. Fit predict on what? We fit and predict on the data, which is DTM LSA, right? This is the SVD data, the data that we have compressed. And we apply it. YLSA, so now, guess what? This object is now like, we've used the algorithm for our DTM LSA, so to cluster our samples. Did that. All right, now let's take a look at the shape and let's take a look at the value. So YLSA, so there's 7, right? There's 7 sentences, therefore there have to be 7 labels, okay? And then YLSA.shape, and it worked, right? Would you guys agree? We had 5 sentences that are one cluster, 1, 2, 3, 4, 5, and then we had the last 2 sentences that just belong to another cluster, and that's it. And so this is, that's it. That's the whole process. So now you essentially have, if you were, let's say you're a company, right? You have some kind of a e-commerce, and you were clustering people into high spenders, low spenders. There you have it. So these last 2, advertise the expensive things because they'll buy them. And then these here, you have to advertise something else. So that will increase your sales somehow, right? So that's kind of the idea. All right. Yeah. So that's the trick. We need to plot it, and we'll do that in a second. But let's go back to the data just for a second. So that's actually up here. So I have machine learning and Python are super fun. Python is super, super cool. Statistics and data science are cool too. Data science and Python are fun. Python is great for machine learning. I like football, and it is great. Football is great to watch, and I like it. So I intentionally played with this data to get really good results, right? If you look, these sentences look a little bit like exaggerated, right? So maybe instead of saying machine learning and Python are super fun, you would just say are fun. You see that? Notice that this is important because here I have super, this is super, but now I've removed one, right? So I had something in common with both sentences intentionally. Now I'm removing it. Instead of having Python is super, super cool, such an exaggerated, I'm just super cool. You see that? So I'm just making, the sentences are less correlated now, right? And we just want to see the effect. So we want them to be more standalone, more unique. Statistics and data science are cool too. Okay, I'll leave that there. Data science and Python, notice Python was referenced here and here 3 times. Do you see that? So I'm just going to say data science is fun. So I'm modifying these. Then I have another Python. Python is, but I've used grade a lot. Have I used grade? No, I haven't, right? All right, so let's leave grade then. Python is great for machine learning. And I've only used machine learning once. Do you see that? So, and then the other ones, I like football, and it is, give me a word that isn't fun or great that we haven't used. I like football, and it is fantastic. Okay, fantastic, right? And then football is great to watch, and I like it. That should be fine, right? Did we use good? We use we haven't used good, right? So let's use good instead of is good to watch. Do you see that? So I'm trying to show you guys that the words, words appearing on the same sentence is really important, right? That kind of, but as I'm removing those relationships, I'm making essentially imagine the sentences are like separating more. So let's see what happens with this. So ran that. I have to rerun everything again. Okay, so this vector changed a little. All right, let's take a look at these values. So they look a little bit different. The negatives are gone, right? Do you see that? There's still a few, but the values did change a bit. Let's see the plot. Actually, it's not bad. Still performs the same. Okay, so they're still too similar. So machine learning and Colab are fun. Let's say that. Let's just remove as many correlations. Python is super cool. Statistics and data science are interesting too. Data science is, have we used fun? Yeah. Data science is useful, let's say. Useful. Python is great for, let's use artificial intelligence instead. And then I like football, and it is fantastic. See, this one, we were using football, but now let's use soccer is good to watch, and I like it, right? So now it's still sports to us, but it's actually two different words, right? So let's see what happens. So I click on green, or click on these. Okay, our values again. See, the spread is bigger, but it's still a pretty good spread. So I'm missing the thing. Fortunately. Let's see if it's still to classification. Ah, perfect. Do you see that? Now I got it to look at that. It actually created, this is actually interesting, right? Maybe you guys can tell me. It created still two clusters, right? But now it's like the first two with the last three, and the two in the middle are their own thing for some reason, right? It's, I mean, I don't know, but visually, maybe these two and that became the cluster. Do you guys see that? And it's just because I was playing with the words, right? So essentially here it's saying that let's see, the third and fourth. So, so these two somehow became their own thing, right? So we had machine learning, statistics is interesting, data science is useful. So the words interesting and useful actually are only being used here, right? And so it's not about like the noun or the noun phrase, right? It's just about the words in this case. Whatever it is, statistics was never used again. These two words have the word data in them, which does not appear here or here. Do you guys see that? So, yeah. So I didn't intend for that to happen, but that's good. That's like a good clustering that happened. Does this make sense, guys? This idea? So obviously, the data, it's just looking at the words. It's co-occurrence of the words. Probably the fact that data appears here and here is significant. And so that helped out in this. Oh, science too, right? So yeah, data science. So that actually was important to determine that those two belonged in one cluster. All right, so hopefully that you've seen that I'm able to produce different results. But let's go back now to the one that I intended to have. So I'm just going to copy the sentences again. And we know that the first 5 are one cluster, the last 2 are another. Let's go back here. Okay. Whatever that is. All right, so let's rerun this, and we should have now the correct label assignment. D. Okay, so this looks similar. And there we are. So the first 5 now belong to cluster 0. The last 2 belong to cluster 2. There we are. Okay, so now the next step, let's just go ahead and plot these so that we can see we have the data and we have the... So we want to do this, and here all we need to do is use the assign labels. So let's take a look at this code. So I'm here just for ease of use. I'm assigning DTM LSA, the whole matrix, this one, to X. Okay, if we print X, all right, we can see that it's a matrix that is 7 by 2. Okay, so our X's and our Y's, essentially, for plotting. And now we have 7 labels as well. So we are going to create 2 scatter plots on top of each other. So I have plt.scatter. And essentially here I'm going to say, I'm kind of like indexing on the matrix, right? On the X matrix. So if the Y LSA is equal to 0, so this is YLSA. So if it's equal to 0, give me those indices. So that's going to be index 0, 1, 2, 3, 4. Okay? So I am doing a Boolean logic on the matrix, right? And I'm looking for the values that match 0, and then it's going to return the index so that I have it. So that's why I'm doing YLSA equal, if YLSA equals 0, okay. And then I'm grabbing from that the column 0 and the column 1. So I can get all the points that are matching the label 0. I'm going to use light green for the color. A marker, I think, is the star, and we're going to call this latent 1. Then I'm going to do the second scatter plot. Second scatter plot, same idea. give me the YLSAs that are equal to 1. All right, so this should return the indices, the last two essentially, 5 and 6, and the value x and the value y. That's why it's column 0 and column 1. And these are going to be marked as orange as far as the point. So these points are orange. And then I'm just going to print the legend and show the plot. So that should be it. And now you can see that's just for plotting, but given the labels, I'm able to see this is one cluster and that's another cluster. And that matches exactly what we, in our minds were also seeing as far as the two clusters. But you can do all this, through machine learning. And this is unsupervised learning. If in machine learning, you wouldn't actually plot it again, like I described, right? So once you have thousands and thousands of samples, they're all kind of like on top of each other when you compress it like this. So you wouldn't use it. But the thing that you would use that would be correct is this, right? The assignment of these labels to each of the 7 samples to indicate if they belong to cluster 0 or cluster 1. Okay, guys? That's the key. Any questions? No questions? All right, so yeah, so that's kind of the idea. This worked really well. So we could try other approaches just to indicate here. For instance, let's try 5. So we're going to do 5 singular value, we're going to use singular value decomposition to produce 5 new compressed columns, right? So we're mapping from vectors, let's say of size 20, the individual words, to vectors of size 5, okay? That might be actually the more realistic. Here we're able to get excellent results, near perfect or perfect. But in another problem, compressing to 2 just so that you can see it may not actually be the recommended approach, right? Because you're likely to lose a lot of information trying to visualize something. So you would still compress to something you can't visualize, like of size 7. All right, so let's try this one. So this is the data. We made it a 5 fit transform. And now we need to specify here that there's 5 of these. So I need to and I'm going to call this one 3, 4, and I need one more. I'm going to call it 5. So a singular value 1, 2, 3, 4, and 5. And there you have it. As you can see, now I have 7 sentences. Each of the sentences is still 1 point, but now it's a vector space of size what? 5, right? So a 5-dimensional space. We wouldn't be able to plot this, but if we do all the processing, right, that would still work. And it may turn, and so later on in the semester, when we look at singular value decomposition, we will see that we actually can calculate how much information is being saved. Other people call it how much energy, whatever it is. It's a metric that tells you're able to, you lost 10% of the information, or you maintain, with this approach of 5, you might retain 90, 95%, so it's still pretty good for your task. It just depends on what you're doing. Here, I can do this one, it's not a problem. I can't plot it, unfortunately. But let's look at K-means. So I instantiate it, and I still just want 2 clusters. So that ran. So I have now 7 values. And let's see, I actually didn't try this before. Maybe it doesn't do as well, but it did. So it still predicts pretty well. So obviously in this example, 2 singular values were perfect, and we can visualize it. Just, I stress it, that's hardly ever the case, right? You can still try a two, maybe three-dimensional, and maybe get some insight, but usually you only get this, and really this is all you want. All right, guys, so that's it as far as this example. Are there any questions? So I introduced a lot of things today of the pipeline of sklearn that you can use, and we used clustering for unsupervised learning. So before we move on to the second example, are there any questions on this one? All right, no questions. So let's move on then to our second example. And I did this one on language first because it's very clear, obvious. Now and so for your understanding, we're going to do almost the exact same thing, but our data is going to be different, right? Our data will now be a cybersecurity data related to, maybe it's malware, you could say, or maybe it's a payload, right, in a packet. So let's go over here. I'm going to close this collab. So I'm going to close this one. Table of contents. Let me change my. Okay. All right. So going back to our code link here. So remember, we're talking about unsupervised learning in KMeans. We're going to click on this one. And I have two examples here. The next example is this one related to network security. Okay. And everything is going to be similar, but it's a new data set. This is my data now. Okay. And what I have here is, imagine this is maybe, let's go with network security. So what do it's network packets again, right? And we're trying to build an intrusion detection system or an anomaly detection system, something like that. And we're going to take this clustering approach. Do you guys see that? So it's going to be a similar example. So here I also have, to keep it consistent, I have 7 payloads that I've labeled normal. But notice there is no actual data, right? It's just me. I know these are supposed to be, I intentionally, right, crafted these. So the first 5 are supposed to be what I would call category normal, and then the last 2 would be an anomaly. So that means maybe it's a network attack. Okay, somebody attacked the network, and the payload had that information in there. So let's just briefly. So these are just hex values, right? And you guys from your courses like 450 and others have, you know that a lot of information is represented as hex sequences. All right, so let's go to the whiteboard for a second. Okay, so. All right, so in a previous discussion, we talked about network packets. And we know, so, we're doing network security, so you have a packet. Right, so you're monitoring your network environment here. So obviously that's the medium where the raw data is coming from. Wireshark, whatever it is, creates a PCAP file, right? And so the PCAP file then has all these headers. So a packet will have several headers, right? Which are usually like 20 bytes in length, something like that, and they contain data. So we're going to focus, let's say, on just TCP packets. TCP packets. So what does that mean? It means maybe that there's an Ethernet header. right? And then there's going to be like an IP header. And then what? A TCP header. Followed by what? A payload header, right? So that's going to be the critical one, which would be much longer too. So we are up to the TCP header, but then you have a long payload, right? Now remember, this of course assumes that the data is not encrypted. So you are building your own system and your own network, so you have full control of everything, right? So it's your bank or your financial institution, so you can have a sandbox area where you take the packets, decrypt them, right? To remove the encryption, and now you just have the data, okay? Because if it's encrypted, you can't do this. All right, so this is, let's call it the payload. And essentially it's the data that's being transported, right? So if there's an attack, like a SQL injection, let's say, or what do you call those, for a buffer overflow, right? Something like that, it's going to be a sequence of hex values, etc. They would be carried in the payload itself, right? So that means that this area here, the payload, is the thing of interest, okay? So we want to know a way to look at the payload for our analysis, okay? Now, whereas in the Ethernet header, the IP header, the TCP header, that was, very established. You had source port, destination port, bytes sent, bytes received, protocol, things like that, right? So that's a standard for the payload to be sent around the internet. But the payload just carries information. I mean, this literally could carry the word, Hammond in there, right? Why not? So the word Hammond could be in there as part of the payload. It's being sent, maybe part of it is being sent, etc. But in this example, we're assuming that what's being carried is, hexadecimal values, right? So there's going to be, so there's Hammond, EF, before D1, whatever, right? FF. Do you guys see that? And you guys know that malware could be sent like this as an exe file, a buffer overflow attack, right? So if you guys have seen that, they have something called a knob sled, which I think is 0x90. 0x90. And these are just processor commands for the for the CPU to do something, right? Take the next step, take the next step, take the next step. So these values look a lot like hexadecimal values because they are in fact hexadecimal values. But the problem here is that there's going to be a ton of them, right? There's going to be a great amount of these hexadecimal values. So if you think about it, it becomes a problem that is very similar to our previous problem, right? Our language before was words in English. There's 50,000, 100,000 individual ones that can form thousands and thousands of sentences. Well, the same thing applies to this. There's going to be a lot of these hexadecimal sequences that are not bad. They're, something related to some process. In fact, most of them are going to be normal, not anomaly. But some combinations of these hexadecimal values are going to be, in fact, related to an attack. Do you see that? Such as the famous knob sled that you'll cover in 450 if you haven't done so already. And so, yeah, that's the idea, right? So if there's a knob sled, for instance, that would be we would want to flag that as an attack. If there is no knob sled, then, And so, yeah, that's what's happening in this example. But we don't know beforehand, right, if something is an attack or not, because we don't have any supervised learning data. All we have is data, right, this hexadecimal data that might look like words and language, and we just can cluster it as normal, anomaly. Do you guys see that? So it's almost like you want to have a distribution, like an average and a standard deviation of what is normal in the environment in terms of all these sequences of hex, And then potentially something that's new, that has never been seen, that could be an attack, will get flagged to be an anomaly. So that's the example. So you can see we did the example before, data science versus sports, and we were able to find those two clusters. Now the question is, can I do the same with just sequences of hexadecimal values where one would be normal and the other one is just other anomaly? Okay, so that's essentially what we're doing in this example. Do you guys understand? Are there any questions about this idea? And this is just meant to be an example. Obviously, you could apply this to tons of other different things. And the great thing is we let the vectorizer figure out the language for us. We don't even have to do that. And there are better approaches, obviously better algorithms that would do that as well. Okay, so that's something else to consider. All right, so now let's implement this. So I'm going to open up Colab again. Colab. Again. Uh, all right, so the same libraries as before, as you can see. So we're using sklearn, pandas, numpy, the count vectorizer, truncated SVD. We're still going to use singular value decomposition, and we want to plot our results. Okay. So here, actually, I do have a different tokenizer. So that's another thing. So before, we were using the built-in tokenizer to identify English words from count vectorizer. But in this example, actually, I built my own, just something simple. Okay, we'll demo this in a second, but it's essentially grabbing every two characters, right? And that's the function. So count vectorizer has this capability that you can define, what specific tokenizer you want. So what are the words in this case? All right, so let's take a look at that. So here I have hex tokenizer. This is a standard approach. I give it text, and notice it just iterates for I in range from 0 to the length of the text, right? And it's going to skip by 2, and then it just slices out 2 characters at a time to build the so-called tokens. Okay? But we just have to define the function, and then we're going to pass this function to our count vectorizer, which is going to be down here. So you can see I'm invoking count vectorizer, but for the tokenizer, I'm specifying that I want to use this hex tokenizer. So it's just going to find individual words. It finds BF, and that's a token. It's not going to become a token again. It just, it just keeps going. All right, lowercase equal false. Yeah, and that's the approach. All right. Okay. What is this doing? Let me see. Let's try this again. All right. All right, so I instantiated the vectorizer. Now, let's take a look at the data. Okay, so let's grab in here. All right, so packet payloads, as I'm calling them, remember intentionally, when I was preparing this example, I kind of intentionally made it, right? So that they are two clusters. But you have to agree that it's hard to tell, right? When we had the words in English, it was easy to tell that we had two clusters. Here, it's hard to tell that these five are supposed to be normal, and these last two are anomaly. Okay, so for us, it's hard to tell, but let's hope that the algorithm can in fact do that. Okay. All right, so remember now these sequences, so something like CC, for instance, or 42, or AA would become now the words like we had in the previous example. Okay, so that's my data. Can I move this over there? All right, so I have the data, I have the vectorizer instantiated, so now I'm just going to fit and transform it. Still calling it DTM, and I'm applying this data set, right? So I can create my vectors. Okay. So far, so good. Now let's print out the feature names that it identified. So from vectorizer, right, get feature names out, and we're just going to print them out. So notice that it identified this as the vocabulary. Do you guys see that? And so that's essentially the trick. So now you have a set of sequences of 2. Maybe you could have done sequences of 3 if you'd like. And now we have a way to say, does that sequence include CC, FF, and 80, and so on, 90. All right, so let's take a look. We can look at this as an array, which is neat. And you can see there's your data, right? So we have essentially, we do have one vector that has a count of 2 for a sequence. 0, 0 maybe. Yeah, there's 0, 0 twice. Maybe. All right, or maybe it's this bottom one, the second one. Oh yeah, it's the second one. Do you see that? So it's essentially how we're trying to solve this problem. All right, now let's just kind of do this in a more presentable way so that we can visualize it even better. So this is going to be like a pandas data frame, but same idea. I take my DTM to array. The rows are still those 7 payloads, let's call them, that I grabbed from the packets. And the get features names out, these are the actual words that I identified. So now I can represent every one of these as a vector of the presence of these things. So I have 0, 1s, I have 32 ones, I have 80 ones, A0, BF, and so on. Do you guys understand? That's the trick. And you can apply this tool for lots of different, whether it's malware or network packets, just different kinds of things from cybersecurity. Sometimes, going from language or images to, a medium like cybersecurity, the algorithms are the same, but what's different is to just make these connections, right? To identify that, yeah, the hex values, for instance, I can just treat them as words, as tokens. And then if you can think that way, then you can start to solve problems in this field of cybersecurity. All right, so let's keep going. So I have obviously my representation of the vectors, but we want to see if it does in fact work. I'm going to do the same singular value decomposition so that I'm going to reduce these from whatever the dimensionality was. I think we had like 12 of them.